All right, we should start. Okay, all right. So today we're happy to have Ilia Shumailov. He's a extremely talented researcher. Got his PhD from Cambridge. Spent some time in Toronto at Vector Institute and Google DeepMind. He's been on the exciting adventure with his startup. He's famous for many papers creating foundation for the current AI security and privacy research, from prompt injection, that is recent work, to mode collapse, to watermarking, to many kind of denial of service attacks. Today, been working a lot on prompt injection, so looking forward to hear from you. Ilia, please go ahead.
Thank you. Let me start off by saying you're overselling me. I don't think
I didn't
that
mention
much.
yet two Nature papers that you have,
No,
numerous other mentions in the media. So I think I saved a little bit for a future.
no. This is too much. You're being too kind. Okay, let me start off by saying I had a very rough night. I couldn't sleep, so that is to say that maybe my English is not going to be as beautiful as it usually is. So my brain is a little bit slow, but hopefully things will still make sense. If you are listening to me and you think that what I'm saying does not make any sense, please stop me and ask a question, because my brain is very slow today.
It's also on YouTube. There is a feature to speed things up, so don't worry.
Oh
Speak
yeah.
at a pace.
Okay.
They will figure it out. So.
No, I think it's more like what I'm saying is not going to make sense, as opposed to me speaking too quickly.
Food for thought for people. Don't worry.
But yeah, you can ping me on email.
Yes.
Right. So the other thing to mention is that I think, unlike other speakers that you're inviting, I'm a lot less academic now. I look at a lot more producty things and engage a lot more with business. So maybe my talk is not going to be as academic. And I'll also broadly speak about relatively sort of old work and try and conceptualize and sort of contextualize and say what I see happening as of today. So broadly, we name this talk "What is going on with prompt injections," in part because I don't know what else to name this. My name is Ilia, and I work at Sequrity.ai. We're building tooling to make AI secure. I think what's sort of on the mind of pretty much everyone in the AI security business community today is what should be happening in the field over the next couple of years. There is a lot of shocks in the market, and some of the shocks are the models are unbelievably good at building things, so the speed at which you can iterate is great. At the same time, models are quite vulnerable, so whenever you try deploying them, things don't really work as well as you want them to. And at the same time, you see there is quite a bit of hype around systems like Mythos, like this omnipotent god hackers that are coming over. And clearly, it's becoming unclear sort of where the security business starts and security business ends. And that's obviously like a big question for all of us. At the same time, if we were to try and predict what should be happening with our models, should our models get better or should they get worse over time? Should we expect that the models will solve their own security issues? That part is very unclear. Like we don't know how to answer that question. And as sort of capabilities grow and people start using models for more and more things, that question should become very important. And obviously, reliability of the models at one point will become critical. And if we use the models in sort of like safety critical setups, then of course you will sort of like have an expectations that they're not going to fail every time somebody is asking them to build something that you don't want them to build. At the same time, we kind of have two outcomes in here. One of the outcomes is, as our AI is scaling and getting better, then it should sort of improve its own security. either through this like mythical dream of self-improvement, or through maybe it's just more data or more compute is going to solve all of the issues, right? And at the same time, the second option is, as capabilities grow, the models get so complex, the capabilities multiply with each other, and at one point, actually security gets worse, and to a point where it gets really hard to find this balance between utility and security. And if you were to try and guess which direction it's going, it's unclear. I feel like everyone I ask this question, they kind of have their own different opinions. Actually, Eugene, what do you think? Where would you bet?
I will bet on the things that better AI will improve the current security, but better AI will worsen something we don't know yet. So that's
Oh, I meant more like security of the models themselves, not applied to security tasks.
but even of the there will be new attacks.
There will be new attacks. Yeah,
Not
I
the
meant
current attacks. The current attacks that do look like
mm.
will be easier to mitigate with time.
So just so to understand what you're saying, you're basically saying as our AIs get better, then the attacks you do with AI will improve as well and become
something like this. Yeah, you can craft more sophisticated attacks.
Yeah, so like Claudini style things.
Something like that.
Yeah, fair enough. This is this is one of the takes. The other takes in the prompt injection community I've heard is models get bigger, and at the same time it seems to be as easy to sort of break them, and you always can find samples that work in unconstrained spaces, and the more functionality they have, the harder it gets to smooth them. So you sort of and as the dimensionality grows, you sort of need to do more and more and more to a point where it becomes infeasible. So it kind of goes in both directions. And funny enough, if you go and try and find academic literature on this point, you'll find conflicting evidence for both of those things. So on one hand, you have OpenAI writing about scaling of robustness with respect to compute, for example. So compute is one of the dimensions where we see improvements in performance for the models. So the more reasoning you allow the agents to do, the better they become. So this is sort of like the reasoning effort parameter inside. And then OpenAI reports that often the models with more tokens are capable of sort of fixing the attacks against themselves. And actually, empirically, you kind of see this. If you use the old attacks against the systems, often the system sort of self-recovers. Attacks works, and then in the chain of thought, it figures out, oh, wait, this was an attack. I shouldn't be doing this. I should do something else. And sort of the attack is stopped. At the same time, there are papers like what you see on the right from some more technical companies and some people we all know from the same community, where folks show that actually, if you show your attacker the chain of thought that the model is experiencing, then your attacks work as well. There is no scaling that you observe, or almost no scaling that you observe with respect to the compute. So in a slightly different threat model, where sort of you're not obfuscating away, like similar to what we saw in the past, like obfuscated gradients, you can actually find the attacks in pretty much the same way. So that is to say that it's just our attacks that are weak, and we're just measuring performance with respect to attacks, and actually not measuring the defensive capabilities of our models. So long story short, we kind of see the same thing. The evidence is conflicting. It seems like there is some scaling in some setups, but also this is not universal, not general, and it's quite hard to imagine the future in all of this, sort of where we will go. So at the same time, more fundamentally, how do we even know that we are actually improving anything in our systems with respect to security? Because it's kind of a chicken and egg problem, in a sense that we need strong attacks in order to tell how well our defenses are doing, and in order to tell that our defenses are good, then we need strong attacks, and they kind of like reinforce each other. So often somebody proposes something, somebody else comes in and says, oh, wait, this attack actually still works. And then another iteration of defenses come into play, and we keep on iterating about this. And the weird part is that we all understand that sort of the lower bound of the spectrum is that the most secure system is the one that doesn't function, right? And obviously this is not what we want. This universal security of completely dysfunctional systems is not great. So we need to find this balance between, okay, we have full utility, zero security, and or zero utility, great security. We need to find how to thread this Pareto curve. And it's unclear because, again, you can't even place yourself in this Pareto curve because you don't know how good your defenses are and how good your attacks are. However, there are some fine folks who do a lot of this analysis and run public competitions, and you can treat public competition as a good metric of the sort of strongest adversaries thus far with respect to the systems. And what they report is that if you take basically pretty much all of the modern frontier models, so the best models one has, plus systems on top of it as well, because it's not just the models that are being run, the pipelines are quite complex right now, you'll find that every single one of them breaks. You can clearly see the gap between, say, like Gemini 2.5 and Claude Opus 4.5 is quite large with respect to sort of the scale of vulnerability, but nonetheless, I think it still remains true that all of them are vulnerable, fundamentally vulnerable today, as in you can find a case where you can force the models to do things that otherwise you wouldn't be, like, the model deployer wouldn't want you to do. We were also involved in a number of efforts of a similar kind, trying to build defenses and sort of analyze failure modes and propose attacks. And in one of the papers led by Milad, Nicholas, and Chavan and Sander, we proposed, let's say today, maybe one of the SOTA attacks you can find out there, where not only did we test all of the recent models, but also we tested all of the recent defenses on top, available both commercially and non-commercially, and pretty much found the same stories what we saw from the Grace One report, where all of them are broken. All of them are broken in a handful of dollars, so not very expensive, and the convergence of these attacks is quite quick. So that is to say that if you wanted to go and sort of attack those systems live, you'll probably be able to succeed. It will take a handful of effort, it will take a handful of attempts, but nonetheless, you will get there. So if you wanted to break those systems, it's still very much achievable, even in presence of the defenses there, both commercial and non-commercial. Funny enough, after this paper came out, maybe a few weeks after, we released another defense paper of our own, something called SIC, and when we ran the RL adversary from the previous paper that broke all of the previous defenses, we found that this adversary does not work against our new defense. And at the same time, it's still, the performance is not zero. The attack performance is not zero. So clearly, this is also not secure. But nonetheless, this cat and mouse game kind of continues, and we need better attacks to sort of advance in defenses, and we need better defenses to advance in attacks. So this inherent cat and mouse game is quite bad as of today, and we're clearly in a great need of building defenses that are sort of coming with provable guarantees, not just heuristic guarantees, because those heuristic guarantees are kind of giving us a very false sense of security at any point of time. And we can always be faced by sort of like a rogue new attack that breaks all of our systems. So sort of like, what does this mean for the security of tomorrow? And I think there are sort of four main lessons from me, especially interacting more with the business side over the past couple of months. One is things are clearly getting better for AI security. Like, I think without doubt today, getting models jailbroken, the frontier models jailbroken, is significantly harder. Like in the past, it was literally like, you poke at it 3 times and this thing breaks. Today, they are significantly smoother. It's definitely like the models are much higher quality. You can still break them, but it's harder. And if this scale continues and the scaling continues in the same sort of rate, I wouldn't be too surprised if we'll get to a point where sort of like quality of service out of our models with respect to security is going to be quite good. I have not really measured the rate of improvement. It's really hard to do because the capabilities are also improving at the same time. And it's hard to sort of distinguish like sort of security from lack of ability to solve a given task. And how to build like metrics of security is a good question. But nonetheless, like observably, objectively, it seems true that things are improving. At the same time, we're still sort of in a space where we have no clue why attacks still work and what kinds of attacks still works. We don't have proper taxonomies of prompt injections. We still sort of broadly put everything in the same basket. We don't distinguish attacks. We don't distinguish the mechanism that they are utilizing. It's still very much a wild west in the academic literature of like why and how things work. And we know that even if sort of tomorrow you make it very hard to break the models, it will still not solve the systemic security issues that those models bring when you actually deploy them. That is to say that, confused deputy problem is fundamental to everything. Your model will likely not have enough context to make a decision. Your model will likely have to make a subjective decision with respect to the information that is provided to it in context. So, like, probably not all security issues are solvable. Probably some classes of prompt injections will remain unsolved, and you will need additional components in order to curtail them. And this is where a bad piece of news comes in. In the market today, security is clearly a competitive subject, and that means a lot of frontier labs are sort of competing in that field. You could clearly see that there is a difference in performance between different models with respect to security, and nonetheless, they're not really sharing how they got the models to be as good as they are. And this is relatively bad for us as users of these systems because, non-universal security stance across them kind of means that we will suffer because everyone is using all of the models, and even if you're not using them directly, you're using it indirectly. So having this sort of a competition in security is not great. It'd be nice if academia figured out how exactly and why some models work better than the other ones, but as of today, it's very much an open question. And it's not a very nice state of the world for all of us, unfortunately. Having said that, we kind of, from 1980s, know that our computers are quite bad and security is quite bad. And from famous FRAC articles from 1996, we know, we have guides on how to break computers. We've been living in a world in which adversaries of different kinds were breaking our computer systems on a daily basis, and the world keeps on spinning. It's okay. So, and it feels like we're kind of back in this world. We know our models are bad. We know they're integrated everywhere, and we know it's quite easy to manipulate them. It's getting harder every day, and it was the same thing with buffer overflows. But nonetheless, we're still sort of in this vulnerable state. And it's okay. I don't think the world will stop spinning out of this. Having said that, we've actually have built systems where we can get some guarantees on security of our model inference. And I think one of the most widely known is the Camel system that came out of Google, mostly work of Eduardo, who was an intern back then, where we were trying to come up with some ways to reason about the deployment and sort of build a principal component where you can reason about the design of the component itself, rather than some heuristic of, okay, I think my model is gonna solve the problem in front of it. Under the hood, Camel does not really do anything fancy or sophisticated. All we do is we separate away planning and execution for a given user task. So we take in a user query and assume it provides enough information such that the model is capable of planning what it's supposed to do in order to solve this problem. And then inside of this plan, it's capable of delegating some tasks to another model. And you can probably think about this as you have some sort of a structured plan. In case of Camel, we implemented it in Python, well, a subset of Python. And then inside of this plan, anytime you need to take some sort of structural output out of unstructured data. So in this case, for example, it's some email, the last email. You don't know what the structure of this email is. You just know that there is some address inside of it. You can take unstructured data, you process it, you make it structured in order for the plan to be executed in a simple way. And then we also build out a separate Camel interpreter where as we're executing the plan that the model produces, this privileged model produces, we also keep track of sort of a dependency and provenance of every single variable involved. And by doing this, you can kind of say that something depended on something else, and then you can say, express sort of rules where you say some dependencies between variables are forbidden. You can say things like, I want to forbid sending an email to people if this email depends on some private information of mine, right? And in this particular case, because we're performing the separation between this, like what we call privileged LLM that does prediction of a task, and the quarantined LLM that does any engagement with untrusted data, you can actually give guarantees, which are similar in sort of a notion to control flow integrity guarantees that you get out of modern compilers. And what that means is the way to think about this guarantee is you can be guaranteed that the task that the user has asked to perform is the only task that is going to be performed, because the actual task that is coded up, that is planned for, is independent, like fundamentally independent of the untrusted data. So if you are independent of untrusted data, then there is no way it should be influencing your execution. To better understand sort of what this kind of looks like in practice, consider this example. I think this example comes from Tau2 benchmark. This is like two bots interacting with each other. I think in this case, the tag was, one bot is asking, I have a reservation I want to cancel it, tell me if I'm eligible for a refund. And the plan that the model constructs out of this query before even interacting with any untrusted data is it says, okay, I've been given a reservation ID, I am getting reservation details, here's all the checks I need to perform according to the policy to check whether the person is eligible. And then each one of those flags is basically delegated to another language model that performs verification of hypothesis that only gives back a Boolean value. So here it basically checks that there is no reservation that has been flown. And then because the whole execution is planned like this, and then all of the reasoning is basically explicitly written out as this stacked if statements, then the maximum that the adversary is capable of doing in this case is manipulating those verify hypothesis outputs. And they can only return a Boolean function, like a Boolean, a single Boolean. So the maximum the adversary can do is sort of flip one of the Booleans, but they cannot force the model to start performing other tasks. So for example, like they will not be able to say, ignore all previous instructions and perform something else. And clearly this is significantly reducing the capability of the adversary. So the adversary at most can manipulate the existing plan and sort of hope that the existing plan is exhaustive enough to include the adversarial goal, in spirit similar to return-oriented programming attacks, but clearly like significantly harder to break. When we build out Camel and evaluated it at first, we basically saw that it kind of solves a ton of the tasks in Agent Dojo that is most commonly used to evaluate prompt injection robustness, or at least back at the time, it was the most commonly used to evaluate prompt injection robustness for agents. And at the same time, Camel, unlike all of the other systems, was actually providing CFI guarantees. So like if a user asks you to solve a task X, no matter what, this is the only task you're solving, and you shouldn't be solving anything else. With, again, a very small caveat that sometimes the user tasks are quite random and user dependent and sort of data dependent. And in this case, is obviously you can't really provide much of a guarantee. At the same time, you're going to talk to security professionals, they will just say, well, actually what we need is a full separation between control flow and data flow. And it's very hard to explain this concept to AI folks. At least I find it very hard to talk about the systems with AI people. And I found another way to spin it and another way to position it, which actually makes it significantly easier to understand. And I reformulate this control flow, data flow separation as task and data independence, right? And the way to think about this is, can you actually, given a task, solve it without ever seeing the data on which you're trying to operate? So imagine you have a Rubik's Cube and you're trying to solve a given Rubik's Cube. And we know how to solve a Rubik's Cube. There is algorithmic solution to it. There is you don't need to come up with it. We know exactly the set of steps we need to do. The only thing that we really require is to know the initial condition under which your Rubik's Cube is based. So you just need to observe some of it. Once you know the initial condition of a Rubik's Cube, you can be pretty much independent of the data. So in cases where you're completely independent of this data, right, it's great. You don't even need to see it. You can just plan the whole action in advance and execute on top of this action, and that should be enough to provide you this control and data flow separation. But in cases where, like in the Rubik's Cube, you do still need to observe some data, no matter what you do, you will have a dependency on this data. And the main question is, how do you minimize the amount of data that you need to depend on in order to make the task sort of task data independent? And this is pretty much the crux of the whole thing for systems like this. And finding this minimal amount of data to release to the planner in order to make the task predictable, or perhaps finding a way to extract this data in a provably reliable way, I think is pretty much the unsolved piece of the puzzle, because for everything else, Camel is actually providing you enough. With the modern models, if you're running on top of Camel, you'll find that this is already kind of restricting the blast radius to a point where your adversary can't really do much. The main question is, for this subset of tasks, which are quite heavily data dependent, how do you turn them into data independent tasks? And some of this is fundamentally unsolvable. So the task that looks something like find my boss's email and follow the steps inside of it is semantically the same as load code from external received data, execute it. And obviously, like, this is not something we can solve. And the best we can do is sort of sandbox this thing. Or perhaps we need to turn back to the user and say, is this the email you're talking about? And then have the user say, yes, that's exactly the email I'm talking about. Those are the instructions I want you to perform. And in this case, this turns a data dependent task into a data independent task. And then the agent perhaps can actually plan the whole thing out and execute with control flow integrity guarantees. But this is the missing piece of the puzzle in all of this. And otherwise, I think Camel is pretty much the correct design for this sort of a thing. Having said that, there is quite a lot of failure modes inside. Like you really should be careful, like, and look out for data flows becoming control flows, right? So for quite a lot of the tasks, the model tries to cheat and build interpreters inside of its plans. So it's basically kind of turns like a data independent task into heavily data dependent task, where it's capable of performing everything. It's like, imagine you have like a stacked if statement of all possible actions, and then you just propagate through it. You basically have like a whole interpreter inside, interpreter pipeline, and this is obviously bad. You may think that running on top of this is very hard, and that should be restrictive. Like, this ability to plan things ahead of time should really be problematic in many cases. Well, turns out the answer is no. We scaled the system to a ton of different use cases and basically saw that actually it works very well, pretty much in all of them. We released the paper together with Hannah and Tom from University of Cambridge, where we scaled this to computer use agents. And those agents are quite complex and problematic because you're trying to do sort of open-ended exploration of the internet. And you would expect that actually trying to predict what your agent should do on open internet is very hard and almost hard to imagine even. But turns out, actually, no, you can get quite good performance out of systems like this. So imagine exactly the same setup as we had before. So you have a user submitted query. There is some sort of a planning exists that tries to find an answer to this to this query, and then we perform just the execution together with just computer use agent. And the tools here, unlike the previous setups, are quite open-ended and semantically meaningless. It's like click on the screen, find the button on the screen, this sort of a thing. And to sort of understand what plans look like, because I was really struggling to at first imagine what the plan would even look like for a computer use setup. It kind of looks like this. So here, for example, it checks, am I on the website currently? Try and find an internal search box. If I've managed to find a search box, then I find an element inside of it. Then I perform a left single click. If the click has been successful, I need to wait for a bit and then perform a typing operation on top of it. And nowadays, I think about this as more like, imagine your task is go and find a PS5 controller on Amazon. Actually, you pretty much know exactly what you need to do. You click on the search bar. In the search bar, you type in Amazon PS5 controller. You get a list of websites from your Google search. You click on the Amazon one. You're already on the page with the PS5 controller. All you need to do is find a buy button, right? So this task is fully predictable, end to end. Today with the models, because they've trained so much on all of this that they understand the structure of these websites to a point where it's pretty much data independent. And guess what? When we run OS World, this is one of the most commonly used benchmarks for computer use agents. That's exactly what we saw. The agent is capable of solving the tasks without ever interacting with the data. Those tasks are completely data independent. And we can solve within 10 attempts, like 65% on average of the tasks. And this is a little bit sort of hard to fathom, because that kind of means that those tasks are data independent. Like, you don't really need to see the internet in order to search the internet for some outcome of your choice. So the tasks we're solving are inherently very simple. And as a result, you don't actually need to show any of this untrusted data with potential malice to the agent. You really just run the agent without all of this data at all. And it's going to preserve your performance. And this is built on top of Camel. So all of this is fully replicatable. Reach out to Hannah. She can share the code if you're interested in this. And internally, we have our own scheme, and we get even better performance than what is shown here. And that is to say that I'm pretty sure this Camel-like setup with control flow integrity, guarantees of security is quite meaningful for even more complex tasks. Like, you can scale it further. It's not it's not a mystery how to do it. Let's keep all of this. At the same time, CFI kind of, as I said, is a very weird kind of a guarantee here. And then it's very hard to sort of imagine, like, how does it break and whether it's even possible to manipulate systems once CFI is in place. And it's quite cool in computer use tasks because you can't really put policies on top of it. You can't really sort of police tools that don't have any semantics inside. And as a use case and a setup to show you a very different class of prompt injection attacks that are not control flow prompt injection attacks, but data flow prompt injection attacks, it's a perfect example. So in all of the plans for web tasks, we found that they all start exactly in the same way. Maybe in part because all of our sort of evals were run in Europe. Every time you open a new website, you get a pop bar with the cookie prompt bar pop up, and your agent, the first thing it always has to do is deal with the cookie prompts. And the thing about cookie prompts is that basically all of the logic to deal with the cookie prompts always appears on top of your plans, no matter sort of where you go. If you look at all of the plans that are produced by the agents, they are always starting with the same cookie bar, and it kind of looks like what you see on the screen. So here the agent is trying to check whether there is a cookie bar prompt right in front of its face, because if it is, then it needs to find how to sort of accept or deny it and keep on going. And you as an adversary, if you know that every single plan that is generated by the agent, every single click to a new web page that is generated by the web page always has a cookie prompt bar, you can actually use this to launch data flow prompt injections. So what we do in this paper is we show that the adversary can basically buy ad space on web pages and plug in cookie prompt bars inside of it, because the agent is explicitly taught to always click on the cookie prompt bars, no matter where it is, right? And you'll find that this is not just like a thing specific to Camel, although it's a nice use case for Camel, but your agent will also do a similar thing, like because they are trained to deal with the cookie prompt bars explicitly on the inside. So what we do in the paper is we inject cookie prompt bars inside of the ads that when you click accept, they lead you to the adversary control web page. And here we show that you can get the agent to basically follow you to another web page that is unrelated to a task. So, and in this particular case, your agent still runs with control flow integrity, right? The plan was to check for cookie prompt bars. It found the cookie prompt bars inside of it. But by clicking on this malicious cookie prompt bars, you deviate the plan execution, a valid plan execution, into an invalid state, and here end up on a spoofed web page. So it is possible to get guarantees of security, in this case CFI guarantees, but we really need a lot more methodological innovation to sort of solve for the rest, like some other classes of prompt injections. And we obviously need to integrate our tooling a lot deeper, because as you have seen in the previous example here, the problem is not the model anymore. This is already like inherent ambiguity in the environment with which the model interacts. At the same time, we really want to police our agents, and policing agents is really hard, as in like you want to be able to express the rules, not just like put them in the prompt, but implicitly say, like, imagine you're an enterprise and you want to make sure that whenever your agent interacts with internal web pages, it does not randomly go and click on cookie prompt bars that send it from internal web pages to external web pages. And this sort of behaviors, they are not a part of the model. They are going to be implicitly a part of the environment in which your agent operates. In Camel, we had a notion of security policies, and those things were like Python code, basically, like arbitrary Python code you could write. It's really hard to use this in case, for example, of computer use agents, purely because the tools don't really have semantics. And like you can't really write something like an agent should not click on a coordinate, because this is quite meaningless. In some context, it should be clicking on a coordinate. In some other context, it shouldn't. It's very much contextually dependent, and you can't really write a security policy like this. And expressing a security policy of when you're on internal web page, you should not be able to click and end up on external web page is very hard to express in terms of clicks. It has to be something else. You have to find some other semantics. And this kind of led us to sort of revisit CSP of the future. And only after I finished designing the slides, I realized that Erlians gave a talk, I think a week before or 2 weeks before or 4 weeks before or something. And he spoke to quite a great detail about Cellmate that we were working on together. Lyoshi and Henry are great. If you're interested in this sort of work, please reach out to them. So I'll skim through this quite quickly. But broadly speaking, we were trying to re-envision what sandboxing for browsing agents may look like in the future, and like enable developers to describe a CSP of the field, as in like some sort of like content security rules of the future, so that you could say express some expectations of what an agent should be doing and not be doing on a given website. And the way we were describing this is thinking about this as like you can have a web developer who is very much incentivized to make sure that the client is safe when they are using your website. Like if you're Amazon, you want to make sure that the agent, like nobody's bringing negative emotions interacting with your website when they're performing purchases on it. So the developer is very much incentivized. In the same way, they're incentivized to keep their website secure with CSP in the first place. They explicitly ahead of time, before the website is released, they describe a set of expectations of how an agent would be interacting with a given website. They register all of the possible web pages plus all of the possible policies that an agent should be following. An example of this policy would be like if you're buying a book on our website and our book is costs $50, then you should not be able to get charged more than $50. And this feels rather obvious, or like it should only be a multiplier on top of this, right? Or if you're interacting on our website and you're performing a purchase of some book, you should not be deviated to some other website. You should really be staying on our website. And if you've been sort of coerced to click on some external link, that means that you've been pushed to this external link in our buy flow, right? And the way we implement this is we describe we perform policing at HTTP level. We basically attribute certain get and post requests to some sort of semantic actions. Then we map those semantic actions to policy names, and inside of those policy names, we put conditions and allowance that are basically conditional on the contents of the web pages themselves. And then the overall setup is basically implemented as a browsing extension, and I encourage the listeners to go and listen to Erlian's talking about this. I think he did a much better job than I am now, just because I'm trying to skip over the content that you've seen already, where basically for a given request, we look up exactly where on the website you are. We pick out the correct policies out of this. We perform checking that for a given website and a given flow, you are not violating any of the policies, and we enable the agent to safely operate on a given website. And turns out the agents today are actually quite good at doing all of this policy selection and argument extraction. They really only struggle in a handful of corner cases, but even then, like, there are some ways to actually fix this as well. So looking in the future, sort of, I think AI security is kind of possible, and the models are already quite good. They're not perfect. They will still fail. They will make mistakes, but it's really tedious engineering plus defense in depth approaches where you build a lot of things. And broadly speaking, I think today, if you're deploying your model on your hardware with your harness, with your environment hooks, and you put monitoring tooling in place, the likelihood of things going wrong is super low. And anybody who tells you otherwise is trying to sell you tooling. And like, I think little by little we're getting there. It's probably going to be imperfect for a while, in the same way as, buffer overflows are still plaguing us today, although they've been around for 30 years. And nonetheless, sort of the world moves on. Yeah, but it's interesting to try and think whether AI system will solve themselves and their own sort of security problems from within the model. But I think the likelihood is we'll just have defense in depth in a lot of different layers and dedicate stuff and sort of maybe actually build a proper taxonomy of what attacks look like and where they fall and what sort of mechanisms they manipulate. And this is a more meaningful direction for the future. Yeah, so I think this is basically the last slide.
Wow.
I hope that was coherent.
That was great. All right. Thank you so much. Yeah. We try to stop it probably. I think that's what